So it is a pleasure to introduce Carlos Ruiz from Colegio Bourbaki, and he's going to be speaking about word embeddings and mathematical logic.
Thank you very much. So first of all, I'm really sorry that I don't have time. I should have prepared the slides. I didn't have enough time. Okay, so I'm gonna talk about mathematical logic and some connections with the kind of machine learning that we are doing in this long-term project with Ernesto. I won't say much about nodes, but many of the ideas that I will talk about today are related to this project. I'll try to get to there. I think it's much easier if I explain this related to, from the natural language processing, especially the word embedding, the models that like word2vec, GLOBE, and all those kind of models. I'm going to concentrate especially on this famous analogy property, that there is an embedding like GLOBE or word2vec, where analogies in English, they are respected in a mathematical way. So there is some kind of linear structure in the induced structure by the neural network inside a vector space, right? So I think that I can explain those ideas a bit better in this context. But everything that I will say, you should eventually imagine this in the world of knot theory. I'm not an expert, so I prefer to talk about this, and maybe that will be a bit more clear. I hope so. And then the other bad news is that even when I will strictly talk about mathematical logic, all the intuition for this talk will come from algebraic geometry, right? So it sounds pretty bad, I know. Mathematical logic, word embedding, algebraic geometry. I try to choose precise statements. So, I will give the idea, but what I would write are all precise statements coming from mathematical logic. So I will assume no background. That's the reason why it's a bit difficult to explain mathematical logic without background. Especially, this is related to something called model theory. Model theory in spirit of Rorschach, Hilbert, and all those people who do applications of mathematical logic. Okay, so I will talk about. So first, I will talk about model theory, and the precise statements that I will write are related to something called pre-geometries, or some people will call these matroids, but those are infinite matroids, right? So I'm choosing pre-geometries so that I don't need to give any background for model theory. So all the statements about pre-geometry that I will say are true, right? So that I don't wave hands too much. I will wave hands a lot, but what I write here, I'll try to make it as mathematically precise as possible. Okay. So then I will talk about a very interesting phenomenon which is called Elekes Sabot. So this comes from combinatorics. This comes from especially from Erdős geometry. But the theorem that I will say, it's a theorem about pre-geometries still, and it's there where some algebraic geometry will happen. It's very basic algebraic geometry. It's algebraic varieties, nothing fancy. Okay, and then I will mention something about additive structure. And when I mean additive structure, I mean inside pre-geometry. So in the language of pre-geometry, this is called modularity. Okay. And here yeah, there will be some notions of algebraic. Okay. I might not get there, but all these things, as I said, is to add in the spirit of today's talk, prior over the architecture, over the definable sets, we will say in model theory, over the closed sets in our, so prior in not theory. Okay. Good. So, I mean, from this point of view, from the point of view of model theory, we're interested in a set. So M will be just a set. You could think about maybe this set. This is perhaps our favorite set right now. And inside this set, or I mean, even some Cartesian product of this set, that would be okay. Even inside this set, we could have different mathematical theories, right? I mean, and when I say a mathematical theory, I mean some axioms about sets here. So for example, I could think about this just as a vector space, right? Of course, in the language of vector spaces. So I have an addition. This addition is the addition as a vector space. And I also have a scalar multiplication. I have a zero inside the vector space, and so on, right? But I mean, this set, as you probably can imagine, is could be a lot richer than a vector space. For example, if you consider a language where you also have addition and multiplication, you could also think about polynomials defined over some field, right? So the family of sets that you could define using a first order formula. By a first order formula, I mean finite string of symbols where variables are elements. So you cannot use variables to represent sets, right? So if you think about a first order formula in this language, you normally have subspaces, right? So, I mean, some affine geometry, some translate of vector subspaces. Well, I mean, and the big difference here is that you have polynomials. So you have Zariski closed sets, and the geometry of those sets is a lot more complicated than the geometry of these sets, right? Of course, I could continue, and I can think about this as an analytic variety. So I can imagine something like the zero sets of analytic functions over the complex numbers. And of course, the geometry there is a lot richer than this one, and it's a lot richer than this one, right? So this is the spirit of model theory. It's always, what you're interested is in the first order logic, first order definable sets, right? So everything that is a finite string of symbols using a fixed language. So whenever you change this language, you will change the geometry and the topology of those sets, right? So I mean, those are three different theories, right? So this is the theory of vector spaces, this is the theory of algebraic geometry, at least the algebraically closed, and this is the theory of compact complex money or complex sum, right? So this is very precise in the if I define properly what a formula is, and then a definable set, and this is an inductive definition, it's a bit boring, but I hope you are all thinking about not only this set itself, but also projections of some Cartesian product, right? Because for example, when you talk about first order formulas, you could always say something like there exists an A maybe in some large Cartesian product of M. So M is our universe, right? So I can all the time I can say there exists an element in a larger Cartesian product such that a first order formula is true inside M with respect to those parameters, right? So this is the analog of just the Cartesian projection in the first in one of the coordinates, right? Yeah. So it's not only this structure. In first order logic, you normally have the structure coming from the rest of the from all the Cartesian products. So if you are like a more modern algebraic geometry, you could think of those definable sets like an analog of the sheaf over an algebraic variety. Right? So we know that an algebraic variety is not just a family of points together with the topology, right? Because otherwise we cannot distinguish curves over an algebraically closed field. And if we think that a curve over an algebraically closed field is just a set together with the topology, you lose all the information, right? You lose all the rational functions into the field, right? So something that is true in some cases is that if you think about fancy algebraic varieties, let's say x and x prime, they are isomorphic as algebraic varieties, meaning they have the same sheaf of functions over some field. It could be an algebraically closed field, even if the family of all definable sets, not just here, but over all Cartesian products, is the same. Yeah. So okay, I have this is my universe, and I'm interested in the shadow of definable sets in larger Cartesian products. Then this will also be, this will respect the real equivalence class, or the real isomorphism class, like an algebraic variety. Okay. Okay. So why this could be interesting for a machine learning perspective? Because whenever we fix a language, for example, let's talk about a language where we have addition, we have like ReLU function, and then you have sigmoid function, and you have some other functions, then most of the neural networks are definable functions in, you need to enlarge the language or something like this, but the architecture itself is encoded in this language, right? So if I am able to say something about sets together with the theory, maybe this information would translate in something about the neural networks using this kind of function, right? And this is something true. I won't give you any details, but it was mentioned before, all this back learning. So this is one of the most important definitions in statistical learning theory. All this back learning, it's equivalent to some property which is called finite VC dimension of the theory where you can define your neural networks, right? So here, by the theory of neural networks, you fix some unary functions, you decide which is your set, you decide which kind of operations you are allowed to do. For example, if you allow product, then you could talk about polynomials, right, which is not normal in neural networks, because this language is enough, right? You have scalars, and that's more than enough. So these are what it's really saying is that if I have the real numbers together with some language, and this language satisfies some property of the theory, this is a combinatorial property, this is true, this property is true, if and only if all neural networks are pack learnable. Pack learnable in the sense, I mean, in this sense that Ron defined before. So it's like a generalization theory, right? What's the problem? The problem is that this generalization theory, in general, it's exponential, of course, right? So it's telling you that you need, if you have n parameters and different parameters, then to have a good approximation in the sense of law of large numbers, then you need exponentially many elements in your data set, right? So those theorems are true, but they won't represent what is really happening in practical machine learning. Yeah. Okay. So I mean that's why this point of view could be interesting for machine learning. I don't know if it's. Is there any question? So something that I have to say is that I wrote here 4 references, which I think could help to read a bit more about the details of the things that I will say. I didn't write a good reference for this, but I will write it after the talk, right? So I hope those references will help. So I don't know if there is any question. Yeah.
There's some tension because you started with different categories and we are on AI and math. So I just wonder if in the end of the road you want to say that the problem with AI is that they don't know how to move from category to category, or what will be the...
So the goal, I mean, the main goal is to explain that there is some mathematical structure coming from logic, which could be used in the same spirit as the prior over symmetries in data sets, the prior over the curvature in machine learning or in data sets, the prior over which graphs occur in the graph neural network. So for example, the last talk when Ron mentioned this temerity theorem, so there is some structure that temerity theorem is giving, and you could add some extra assumptions to this combinatorial structure, so that this ends up being a prior of your architecture, right? So I mean the main goal is to explain that there could be a reasonable new idea coming from mathematical logic that could be used as a prior, right? So in fact, I could explain what VC dimension means in terms of which is the version of similarity regularity lemma for those theories. So it's something like in similarity regularity lemma, all possible graphs are not easy, but are less complicated if and only if the theory has finite VC dimension. Yeah. Good. The second part, and I know there is tension, and I mean, it's natural because most of those things are very difficult to state as a theory. I mean, we could work some things together with Ernesto, but I mean it's a hard problem. Okay, so I mean, if I won't say what a theory is and what a model is, at least I should say some combinatorial definition, which in very restrictive cases it's the same as a theory, right? So I said that M and a closure operator is pre-geometry if the following easy axioms happen. So this is like the definition of a matroid. You should think of this as a vector space. You should think of this as the vector subspace generated by some set. In the case of the vector space language that I mentioned. But for example, if you think about the field structure where you have the algebraic geometry, then this closure operator is the algebraically closed field generated by. Yeah. Okay, so if this closure operator satisfies some very easy properties, so the closure contains A, so it's monotone. If A is containing B, then the closure of A and closure of B. So I think, there is another property, but it's quite clear if you think about this closure operator as the vector space spanned by this. So it's a finite character, meaning that if you have an element in the closure of some arbitrary set, then there is a finite set inside A where it's contained. So this is where the first order theory comes from, because what I'm saying is that if I have a Zariski closed set, then there is a finite set of polynomials which define this Zariski closed set, right? Okay, and the other property is very strange. So this is called the exchange principle, and in the second reference that I gave you, in the appendix is proof that vector spaces, algebraically closed fields, projective planes, they also satisfy this property, which is not immediate. It's a bit weird. So if A is an element in the closure of A union B, but it's not in the closure of A, then B is in the closure of A in A. Okay. This the first time for vector spaces is very easy, especially because you have a commutative group, but for algebraically closed fields, this is a bit an strange condition.
So what is A sub F? A sub F comma A. Yeah, on number 2 condition. What is this A sub F?
Sorry. So there is a finite
okay.
subset where you could define. So this finite subset is essentially the parameters, the coefficients of the polynomial that define it. So this is the first order theory that I was pursuing. Okay. So as I said, we have many examples. If I have a vector space together with this span operation, this is a free geometry. If I have, for example, if I have an algebraically closed field, so let's say, I always say M for my universe. So if I have F, an algebraically closed field, the algebraic closure, in the sense of algebra, in the sense of polynomial, is also a free geometry. Okay. And then you have many kinds of free geometry. So for example, if I have a complex torus, so M is a complex torus. So all those things, they look like one dimension of things, right? But the thing is that some structure over my set could live in a larger dimension. So, for example, a complex torus, an algebraic variety could live in a larger dimension. It could be of algebraic dimension larger than 1, right? But if you restrict to some of the subsets inside, then this is a free geometry, right? So here I mean analytic subgroups, right? So it's difficult because I define a pre-geometry as this closure operator, and here I'm saying analytic subgroup. Of course, what I mean is the closed sets under this operation. It's a bit more intricate to define exactly the closure operator, but I think you could have a good idea of what we mean by this, right? Okay. So the good thing about these pre-geometries is that you have a notion of dimension. Okay. So and this is thanks to this axiom that it's possible to define a basis. So a basis is just a minimal set of elements where you could define the closure of the set. And in particular, the definition that we are more interested is modularity. So you say that pre-geometry. So pre-geometry is modular if and only if the dimension of A union B is equal to the dimension of A plus the dimension of B minus the dimension of the intersection. Okay? So this property is trivial, for example, for vector spaces, right? But for example, this is not always true in algebraic geometry. So in algebraic geometry, this is the smoothness here. If you look at the this is like some kind of smoothness from the algebraic variety. Okay. So the idea is that in mathematical logic, the prior or this axiom for the theories, this dividing property for the theories is modularity. So you could say many things about modular theories. So modular theories are essentially vector spaces together with some extra structure, and it's very nice because you work only in this abstract setting, right? And then you recover something concrete like a vector space or a vector space or something. Okay. Good. So, so the result that was proved by Eleke-Sabot, and this is, I believe, the very good reference that could help you to see some details, not coming from model theory, and this is just from a combinatorial point of view, tells you something like this. So assume that you have V, an algebraic variety inside this. Let's say this is an algebraic variety. And assume that you consider pre-geometry over this algebraic variety. So V is equal to M. And in principle, I won't say anything about what this closure is. It's arbitrary, and that's the interesting part. It contains, for example, addition. It could also contain something that it's outside the theory fields, right? So this result tells you that this set or this pre-geometry is modular if and only if V is almost the same. So here is a bialgebraic correspondence to the graph of the addition inside some algebraic group. So G, it's an algebraic group. Okay. So this theorem tells you that there is a combinatorial definition of the induced structure coming from an induced abelian structure coming from an algebraic group. So this is very close to something called the theorem classical theorem from algebraic geometry. So you have some structure with some extra actions, and you want to recover the algebraic geometry from from this few sets of axes. Okay, so this term was proved by Elekes and Chabot without knowing anything about model theory. If you want an explanation of this result closer to probability theory, there is a very nice blog by Pernstall. So he explains this result just using a random variables. Yeah, I mean this result is true in algebraic geometry. I mean he needs random variables over an algebraically closed field, and this is quite restrictive. Okay, so I don't know if there is any question.
What is gamma again? Is graph?
Yeah, so this is the graph
The graph.
of the addition function. Addition function inside this algebraic group. And what is interesting is that this theorem, I mean, there is a generalization of this theorem where you have any set here. And the generalization tells you that even if it's not the graph, this set is just cosets of an algebraic group, right? I mean, because you don't live in C3, then this is not a graph, but all the structure comes from the addition inside an algebraic group. Okay. Yeah. Well, okay. Yeah. In this case, it's commutative algebra. So what I will say right now is a technical proposition called the group technical theorem called the group configuration theorem, which explains this Elekes-Szabo phenomenon. Which this will be a link to this closure operator, and this will give you some idea of why those results could be stated at least in a purely probabilistic point of view, right? I mean, just think about random variables and this kind. So assume that you have some group G. So think of this. I mean, I always think about an algebraic group, of course. But let's say you have G, an element here, F, an element here, and this is true even if you think about a group acting on some set. So I will say that I have V here, so G acts on V. So I have a linear equation into the image G of V, right? So this line means that there is a linear relation between those three elements, right? Of course. Yeah. So here I also have a linear relation between those two elements. So here I should write something like G minus 1 F. So there is, you agree that there is a linear relation between those two elements. And if you're inside a group, you agree that there is also a linear relation between those three elements, right? Yeah. So it's, no, it should be something like this, right? So G times F minus 1 V, no, sorry, F V, it's just GB, right? So inside the group, this is always true. This is trivially true, right? Even inside a group acting on a set. You could think of those elements as a set, and you have a group acting on a set. So those relations, those combinatorial relations or those dependence relations, they are always true, right? Inside the group, if you have this structure of an addition. So the group configuration theorem tells you that this group configuration tells you that every time that you have a pre-geometry together with a sextuple, together with 6 elements satisfying those dependence relations, then it's because there is a group. That's a group configuration. So it's a purely it's a characterization of groups in terms of dependence. Right? So here I was talking about vector independence, algebraic independence in the case of fields, but of course you could also think about the statistical dependence coming from some data set, right? Yeah. So you could think about like a Bayesian network or something like this, where you have some kind of diagrams telling you which element is dependent to which element. So, and actually, that's the way turns down his blog explains this group configuration here. Okay. There is any question?
That's where the randomness comes in the ability to see it as a Bayesian network.
I mean, what I'm saying is that this is purely combinatorial. There is nothing statistical. There is no random variable. But those diagrams, they also have a meaning in a probability space, right? So if you think about like the conjugate, the joint distribution of the representation. So what I'm thinking about is, so imagine that you have an element in R300. So this is the 300 dimensional vector representing a word in Word2Vec, right? So, I mean, now think about the statistics, not just this, but think about the statistics of some sequence of words. Right? So, I mean, those kind of, I mean, if you think about in a real data set, if you think about this joint probability with respect to the dependencies, you fix what do you mean by being dependent or something like this, then you have these kind of diagrams, right? Yeah. So I should be careful because this theorem is not for any probability space. So this theorem is over algebraic varieties or over pre-geometries, right? So I mean, the precise statement is not true in any random variable setting. You need the field structure to make this statement. The statement, this is the characterization, the combinatorial characterization of a group. You need a bit more. Yeah. But I mean, it's conjecture in model theory that there is a probabilistic version of this theorem, and that one is people don't know this. Okay. So, I mean, why this could be interesting to have such a result? I don't like the example of the king, queen, man, woman. So I will say something like, you have a word for LSTM, and then you have a word for translation, and you have convolutional neural network is related to object detection, right? So maybe this analogy is a bit more interesting. So, I mean, what does Word2Vec would tell us about this this relation? Well, it essentially tells us that the word, the vector representing LSTM minus the vector representing translation plus object detection. This is linearly related to the word representing convolutional neural networks, right? Okay, so it's a bit of a surprise that if you add this to this, you recover this other part, right? So I will write this as an operation that might not be the operation inside that might not be, sorry, the addition in the vector space, right? I mean, this is something extra that we are getting in statistically in machine learning, right? But just the fact that there is some closed operation that it's also respecting this addition, I mean, this is something remarkable. If I tell you that there is a group structure, maybe it's not the group structure coming from the 300-dimensional vector space, but just a group structure inside this space. I mean, if I can make a precise statement saying that this is a group, that for some family of the words in the language, there is a group, this will be something non-trivial, right? I mean, but those kind of theorems, they also help you to recover the actual addition from the vector space. So, I mean, this is something common. You need to work a bit more. You need to work a bit, getting a known addition function, a known group structure coming from an abstract group structure, you need more work, even in the algebraic geometry case, right? But, I mean, just this statement could be interesting, right? Okay. So in some sense, there is a feeling that a modular structure is witnessing this statistical dependence relations between some of the elements in your vocabulary. Okay. So why would it be interesting to have such result? Because if this is true, in model theory there's always a bigger dimension analog of this result, as I mentioned, right? And I mean this point of view came to my mind because one time I was explaining wrong this article. I was explaining this article to my students, and I did a mistake. So there, they find an analogy between this element and I think HCP. So this is, I don't know anything about this. So this is a chemical element, and this is some crystallographic structure of this element. Okay, and you also know that this CR is related to BCC. I mean, in this article, they found that the analogy property, this analogy property is also respected when you train your word-to-vector model in material science text, right? So I read there that not only this was true, but also there was some ternary relation, something like RO2, so the oxygen of this element, and CR2O3. And I just memorized this, right? So, I mean, it's true. I mean, that's the observation. The analogy, this analogy is satisfied. And it's true that, it's also true, sorry, that this analogy is satisfied in the same sense as the traditional analogy for debate. And this is remarkable because the data set is a lot smaller, right? But what I read is that there was a relation between this word, and this word, which was also respected by this word, and this word. So not just a linear relation between those pairs, but a ternary relation. Actually, I'm not sure. I've never seen something like this that it's proved statistically. I know that those relations are quite easy to verify, but I mean, whenever I have three words, then I could also be interested in the dependence between between a pair of words in the presence of two other words each, right? Of course, there is no order here, right? So I'm not saying that these kind of ideas could be used in a sequence model, right? But at least the other models like latent digital allocation, where you have this exchangeability property, where you just care about the presence of words regardless the symmetry group. So I mean, if this modularity is at least statistically observed, those theorems could tell us something like this immediately. Okay. Is this clear? Is this example clear? Okay. Okay. I mean, I think that it's very interesting to check if we could make this statement precise. So I know that, for example, for alert language, yeah. No.
It's not related to what you just said, but right before. So do you think by assuming some kind of structure like this, it would be possible to get representation of data like embeddings with train this kind of embeddings with smaller amounts of data?
Yeah. Yeah, exactly. I mean, that would be one of the goals. Yeah. Okay, and I think that I'm running out of time. Okay, so what would be the idea if we want to use those priors in another neural network, right? So here is a bit different because it's not enough to change the language, but we need to change the language so that the pre-geometry is satisfies our modularity, like, yeah. Because I mean, what we have here is, perhaps I should say this in a more precise way. So you have your neural network here. You have the output. And whenever you have a language, what you're doing is in some latent some number of latent variables. Right here, 300. Your data set and the architecture, and I mean, when I say the data set, of course, I say all those dependence relations. It's inducing over inside this vector space. It's inducing a new structure that might not be the whole. I mean, it's not the power set, right? Here we have some particular dependence relations between those words. Yeah. So this, of course, the difficult part of this project is that there is no machine learning, or at least that I know, there is no way to control the induced structure just using language, because you also need the statistics of the data, right, to make those kind of statements precise. Okay, so I mean, how could we use this in a project like the one Ernesto talked about? I mean, we need to 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 say how those embeddings are supposed to work with respect to the problem that we want to solve. Right? But this is the hard part. But if we are able to add this extra assumption to the latent space, then we hope that maybe we want to solve a problem for all nuts, but at least some class of nuts, which is a bit smaller. So I think that's up here. Sorry. But
Any questions?